There's a region of space, roughly 330 million light years across, containing almost nothing at all. No galaxies, no stars, barely any matter of any kind. Just an almost perfect void sitting inside the largest structure in the entire universe. It's real, it's been mapped for decades, and a brand new telescope that just started operating in Chile a few weeks ago is specifically built to find thousands more of them. One quick correction before we go further, though, because it matters. Vera Rubin Observatory hasn't announced discovering a specific new one of these yet. Its survey only just began. But the actual science here, what these voids are, how strange they turn out to be once you study them closely, and why Rubin is about to change this entire field, is genuinely more interesting than a single headline discovery would be anyway. Stick around, because I'm going to walk you through exactly what these enormous cosmic voids actually are, what the most recent detailed mapping efforts have found hiding inside them, and why Rubin Observatory is about to become the most powerful tool ever built for studying them. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the largest survey telescope ever constructed. To understand why these voids matter so much, you first need to understand the structure they're actually a part of, the cosmic web. Galaxies throughout the universe aren't scattered randomly through space. Gravity has organized them, over billions of years, into an enormous interconnected structure of filaments and dense clusters, threading between regions that have been slowly emptied out as their matter drained away, pulled by gravity toward the denser structures nearby. Those emptied out regions are cosmic voids, and they're not a minor feature of the universe. They make up the overwhelming majority of its total volume, vastly larger and more common than the comparatively crowded filaments and clusters that thread between them. One of the largest confirmed examples, called the Boötes Void, spans roughly 330 million light-years across and contains dramatically fewer galaxies than the surrounding regions of space. A genuine, enormous gap discovered decades ago and confirmed repeatedly since. For a long time, voids were treated mostly as the empty leftover space between the genuinely interesting parts of the universe, worth noting, but not worth studying in exhaustive detail on their own. That's changed considerably in recent years, as researchers realized these voids aren't simply empty. They're a genuinely valuable scientific tool in their own right, precisely because they're empty. If you're finding this as fascinating as researchers clearly do, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. Here's why that emptiness turns out to matter so much. Voids are considered some of the cleanest, most sensitive available probes of dark energy, the mysterious force believed to be responsible for the accelerating expansion of the universe. Because voids contain so little ordinary matter, the physics governing how they grow and change, shape over cosmic time is comparatively simple to model, less complicated by the messy, difficult to predict physics of galaxy formation and stellar evolution that muddies measurements taken from denser regions of the universe. That relative simplicity makes voids an unusually precise tool for testing exactly how dark energy behaves, and whether it's been constant throughout cosmic history or possibly changing over time, a genuinely open question at the center of modern cosmology. One of the most detailed recent efforts to actually map this structure came from the Dark Energy Survey, published in 2024 by a research team that included cosmologist Niall Jeffrey at École Normale Supérieure in France. Using data collected from roughly 100 million galaxies, the team built one of the most precise maps ever created of both the visible cosmic web and the underlying dark matter scaffolding believed to shape it, tracing out the enormous voids and dense filaments connecting galaxies across a huge portion of the observable sky. That kind of large-scale mapping effort represents exactly the type of study voids are uniquely suited for, converting simple galaxy positions into a genuine three-dimensional picture of the universe's large-scale structure, void, and all. What makes this an especially exciting moment for void research specifically is what's coming next, and this is where Vera Rubin Observatory actually enters the story properly. Rubin, perched on a mountain called Cerro Pachón in Chile, began its full 10-year legacy survey of space and time on June 30th, 2026, following years of construction, testing, and a gradual commissioning process. It uses an 8.4-meter telescope paired with the largest digital camera ever built, and over the coming decade, it's expected to catalog roughly 20 billion galaxies across the entire visible southern sky, repeatedly imaging the same regions over and over to build up an enormous three-dimensional record of the universe's structure. According to researchers specifically focused on void science, that scale of data represents a genuine transformation for this particular field, combined with a separate complementary survey called DESI, the Dark Energy Spectroscopic Instrument. Rubin's data is expected to enable void studies covering a cosmological volume far larger than anything currently available. unlocking what researchers describe as transformative potential for the field. Part of what makes that increased scale so valuable involves a specific limitation current void studies still struggle with, actually seeing what's inside them. Voids aren't perfectly, completely empty. They contain sparse populations of dwarf galaxies, small faint galactic structures that are considerably harder to detect than the larger, brighter galaxies that populate denser regions of the cosmic web. According to researchers studying exactly this question, next-generation surveys like DESI and Rubin are specifically expected to detect tens of millions of additional galaxies, enabling void characterization with a level of precision current instruments simply can't match, particularly when it comes to detecting these faint, void-interior dwarf galaxy populations that remain largely invisible to existing telescopes. Understanding exactly what does and doesn't exist inside a void, down to its faintest, most sparse contents, is central to using voids properly as a precision cosmological tool, rather than treating them as simple, featureless gaps in the map. There's also a technical piece of Rubin's design specifically built with this kind of low-density, faint object science in mind. According to researchers planning for Rubin's low-surface brightness science program, the observatory's 10-year survey is expected to revolutionize this entire category of astronomy, transforming scientific understanding of extremely faint structures, including the sparse, dim galaxy populations that inhabit voids, precisely the kind of target that's difficult or impossible to study using a single, quick observation, but which becomes achievable once you combine hundreds of repeated observations of the same patch of sky across an entire decade, exactly the kind of cumulative, long-term dataset Rubin is specifically designed to build. It's worth being clear about the current state of this specific story, since a lot of individual pieces are moving simultaneously right now. Rubin's real-time alert system only went fully live on February 24th, 2026, immediately flagging roughly 800,000 changes in the night sky during its very first night of operation, and the full 10-year survey itself only formally began a few weeks ago, at the end of June 2026. That means the enormous void mapping datasets researchers are specifically anticipating from this observatory are still in their earliest stages of being collected, not yet available in the kind of complete published form that would support a specific new discovery claim about any single newly identified void. What's genuinely, verifiably true right now is that the infrastructure capable of dramatically advancing this entire field has just switched on, and that researchers across cosmology have spent years specifically preparing to use exactly this kind of data the moment it starts arriving. It's worth explaining why researchers are this excited about a discovery that, in a literal sense, hasn't happened yet, because the anticipation itself reflects a genuine, well-founded understanding of what this instrument is capable of. Jeffrey, discussing the broader trajectory of this field following the Dark Energy Survey's 2024 mapping results, specifically pointed toward Rubin Observatory alongside the European Space Agency's Euclid mission as the next major leap for this kind of research, predicting that combining data from both projects would allow scientists to build even more exquisite maps of dark matter than anything currently available. That's not idle speculation. It's a reasonably confident prediction based on the simple, verifiable fact that Rubin will eventually collect a vastly larger, more complete dataset than any previous survey has managed, covering a wider area of sky to a greater depth with more repeated observations than any instrument that came before it. So what does all of this actually add up to? Enormous, genuinely empty regions of space really do exist, stretching hundreds of millions of light years across, forming the overwhelming majority of the universe's total volume, and functioning as some of the most precise tools cosmologists currently have for studying dark energy and the large-scale structure of everything around us. Vera Rubin Observatory hasn't yet announced discovering a specific new one of these voids, since its full survey only just began a few weeks ago, but the entire scientific community studying this exact topic has spent years specifically preparing for the moment. This telescope's data starts arriving precisely because of how dramatically it's expected to expand what's currently known about the emptiest regions of our universe. If stories like this one, grounded in real published research and honest about the difference between what's already been discovered and what's still being anticipated, are what you want more of, subscribe to this channel and turn on notifications, because Rubin's 10-year survey has barely begun, and there's a real chance the next few years bring exactly the kind of void discovery this story is currently just setting the stage for. Thanks for watching, and I'll see you in the next one.